It's science, but not as you know it. The Naked Scientists.
Hello, welcome to The Naked Scientists with me, Chris Smith, and also with Helen Scales.
Hello.
Now, in the programme this week, we're going to be finding out how a dynamic duo comprising a mongoose and a robot are helping to clear minefields much more quickly. Also, raindrops on roses. I won't sing anymore, but scientists have discovered why dewdrops cling on to rose petals. Don't they look pretty? And also, it's on the tip of my tongue. We've all had that experience of not being able to find the word we want, but why does it happen? And how can you stop it, more's the point. That's all on the way. Helen.
Thanks, Chris. Also this week, we're looking at the science behind the sparkle, because we're delving into diamonds and other precious stones to find out how they form, how they can be faked, how to spot a dodgy diamond, and how they can be used to make high-powered lasers, cutting-edge scalpels, aha, and even superior-sounding speakers for your hi-fi. So that's all on the way. Plus, in Question of the Week, we'll be drilling for the answer to this.
During the 1970s, we were told that oil would run out by the year 2000. Then new reserves were discovered, and now they say 2100 is when we will be starved of oil. Is it possible that we'll find more oil reserves in time to come?
And obviously the answer to that question doesn't apply if you live in Grangemouth in Scotland. It could be a bit different under those circumstances. Thank you, Helen. So if you've got any questions for us about the science of diamonds or other geological marvels, then do get in touch. Email us, chris@thenakedscientist.com.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider. On the web at ukfast.net.
Well, let's take a look at what's been happening in the world of science around the world so far this week. Very exciting is this paper, which has been published from engineers at the University of Moratuwa in Sri Lanka, and they found a very quick way to deal with landmines, the potential problem of landmines. Helen, how many landmines do you think there are around the Earth?
Oh, gosh, probably an awful lot more than we expect. Oh, I don't know. 50 million.
You're in the right ballpark. It's 110 million landmines lurking in the ground in about 68 countries. That's according to the United Nations. So big problem. They're very, very cheap to plant. Cost about £1 to plant a landmine. To get rid of them is a very different problem. £500 per landmine that you want to clear, because the best demining personnel can really only deal with something in the order of 2 square metres of minefield per day. And the big problem is finding out where they are. They're also often in countries which have just got over wars and things, and they want to get their economic production back up, but these landmines are all over their agriculture, so they can't go and farm the land, and therefore they can't feed people, so it makes the country stay in turmoil. So dealing with it, we need a solution. And there's a group of researchers in Sri Lanka. The lead researcher is Thrishantha Nanayakara, and what he's come up with is a robot which is tethered to a mongoose. So you have a mongoose on a lead that's linked to this robot, and the mongoose has been trained to sniff out mines. Mines contain TNT, trinitrotoluene, and when the TNT inside the mine breaks down, it oozes bits of TNT into the soil, but it also breaks down and produces nitric oxide and nitrogen dioxide. And this goes up to the surface where it can be picked up by things with sensitive senses of smell. And mongooses, which are like a giant rat really, can smell it. And they've trained these mongooses to, whenever they smell the smell of TNT or these oxides of nitrogen, to stand on their hind legs and sniff the air, so it pinpoints that patch of ground as to where there might be a landmine. So the robot has got a video camera which watches where the mongoose is going, and the robot leads the mongoose to make a systematic and thorough search of an area to make sure no areas are missed. The mongoose stands up and points out where the mines are, and then the researchers are watching all this, and they're putting X's on a map so they know exactly where to focus their demining attention.
That's really clever, because I know there are things like they do use giant rats in Africa, I think, to spot landmines, but I like, obviously it's the idea that they need to be controlled, otherwise they just run all over the place. They need to go in certain spots, and that's what this robot is doing, is making sure it's thorough. Do it thoroughly.
And the other good news is that the price tag is about $3,000, so £1,500. It's actually very cheap compared to humans and sniffer dogs, which are much more expensive. But also the robot mongoose combo weighs less than 10 kilos, which is not enough to set off a mine. So
you're not actually
you're not going to harm the animal, we hope.
Oh, that's good. That is good news. So, Chris, here's a question for you. What are your favourite things, or some of your favourite things?
Sleep, which I don't get much of. What else? Weather, good weather, doesn't have much either. Low oil prices, that's definitely not happening.
That sounds good. Well, later today we're talking about precious gems and diamonds, which could well be some of your favourite things. Well, I rather like whiskers on kittens, but if you go in for raindrops on roses, then here's some news for you. A study has come out this week that reveals why it is that drops of water cling to rose petals in that most beautiful of ways. Lots of flowers and leaves are actually covered in spines and a layer of wax, which makes them repel water. So it actually slides off and takes dust with it, a process known as self-cleaning. But this doesn't happen in roses, where the water droplets actually cling on instead. And now scientists from the Tsinghua University in Beijing have worked out what's going on and how this happens. Now, rose petals are actually covered, it seems, in spines, but they have no wax. And the way that those spines are arranged in rows with quite wide furrows in between them means that the water droplets are kept in quite spherical balls, and they're actually held onto and basically cling onto it on the petal surface. And what's more, the team has cast a rose petal out of polyvinyl alcohol and found that this man-made substance that's the same shape as the petal has exactly the same properties and clings onto just the same amount of water as a real rose petal does. So it's a bit like gecko's feet, where the stickiness of petals and gecko's feet is all about their physical structure, not so much about the chemical composition of what they're made out of.
That's very nice, but why is it important to spend scientific budgets on researching rose petals?
Well, this is true. I mean, it's nice we know that possibly for roses it's a good thing, because it might be that these twinkly rose droplets, water droplets, actually attract pollinating insects.
So attract humans.
Indeed, and they are lovely. But scientists may also be able to use this kind of understanding for things in laboratories where you need to keep tiny amounts of liquid separate but move them around in a very small area. I think sort of it's complicated stuff that this might kind of, in a lab situation when minute amounts of fluid can be used.
So when you say attract pollinating insects, it's because it can give them a drink? Because they can go in and they're attracted to the water?
It could be. Just maybe because they just see them and it's more obvious. Because lots of plants have things like UV that we don't see but that insects see, and there are lines that guide them in to where the pollen is and all the juicy nectar and so on. So yes, it's rather sweet. But yes, you're right, it's a bit slightly strange, but why not?
Now, do you get frustrated by wanting a word sometimes and you just can't get it?
Yes. Indeed.
Now, it's called tip-of-the-tongue experiences, and people are fascinated by this because we want to know, why does this happen in your brain? What's going on? Why is it that you know what the word is, you know the word, but you just can't make the movement that you need to say the word? And it's very frustrating. In fact, it ranks on a world list of most frustrating things as quite close to the top, actually. And researchers at McMaster University in Canada, Amy Warriner and Karen Humphreys, wanted to find out what the best thing to do when it happens is. Because do you ruminate over it and try and work out what the word is, or do you go and get someone to put you out of your misery quickly? And this is important because there's this idea that we learn by our mistakes. So if you don't know a word, does not knowing it and the kind of embarrassment of being tongue-tied and then having to be helped out with the word, does that mean that you then don't make the same mistake again? Or is it the way round? Are you learning your mistake better than actually getting it right? And so what they did was to recruit 30 students at the university. They put them in front of a computer screen on which there were statements which were carefully selected to provoke them to want to say words which were known to be tip-of-the-tongue type words. So you might, for instance, show someone a picture of an armadillo. Most people know what an armadillo is. They know what it looks like, but it's one of those words that you think, oh, what's the name of that thing? And that's the tip-of-the-tongue experience. So they showed them these statements or things that were designed to provoke this experience, and they then had to press one of three buttons. Either they knew the word that was being elicited, they didn't know it, or they were in tip-of-the-tongue territory. And if they pressed the tip-of-the-tongue button, then the researchers waited either 10 seconds or 30 seconds before putting them out of their misery. Then, after they'd logged all the words that provoked tip-of-the-tongue, they then waited 2 days, and the students came back, same students, did the same test, same words, and on some of those words, there were, again, tip-of-the-tongue experiences. So they didn't learn from 2 days previously, probably because they're students. But the interesting thing here was that when the researchers looked, they found that when they had made the students wait 30 seconds worrying about what the word was before telling them, they were much more likely to have another tip-of-the-tongue experience on that same word the next time than other words when they put them out of their misery much more quickly. So what they say is it's a bit like spinning your wheels in a snowdrift if you are worrying about what this word is, because you're basically reinforcing the nerve connections that are wrong, taking you down a sort of blind neurological alley where you can't find the word you want. And by going over it and over it and over it, you're actually making those pathways stronger instead of strengthening the connection to the word. So their solution, get someone to help you out quickly, stop worrying about it, or look it up on the internet if you can.
I always find it with names. That's the worst thing. When I know someone's name, but it just escapes me, and that's so embarrassing when you're looking at them and you know their name, but you just can't get it out.
There is a condition called prosopagnosia, which is caused by damage to a part of the brain called the temporal lobe. It's in the top part of your temporal lobe, and people cannot recognise faces.
Oh, yes, yeah.
So you can show them a picture of their own wife, who they've known for 30 years, and they cannot recognise the person until the person starts to speak, or they look at their clothing, or some other giveaway. And they just can't do it from faces.
Yeah, fascinating stuff. Now, we know that many reptiles, like crocodiles, can choose the sex of their offspring by controlling the temperature that the eggs are incubated at. And now it has been revealed that human mothers might also have some influence on whether they have a girl or a boy, not by controlling temperature, but whether or not they like to enjoy a bowl of cornflakes for breakfast. That's what researchers from the University of Exeter here in the UK have found when they carried out a survey of over 700 expectant mums who didn't know whether they were carrying a girl or a boy, and by asking them about what they ate around the time of conception. And Fiona Matthews discovered that women who ate at least one bowl of cereal a day were more likely to have boys than women who frequently skipped breakfast. And this sort of thing has been noticed before. It's quite an interesting phenomenon, actually. During sort of wartime and times of stress and crisis, like the 9/11 bombings and earthquakes and things, quite often, if you look very carefully at the number of boys and girls that are being born, you do see a very slight increase in the number of girls being born. And there's lots of ideas for why that might be. And in fact, there is a global downturn in the number of boys being born, ever so slightly, by about 0.1% since the 1970s. Which
is that because we're all better fed?
No, we're getting increase in the number of girls, which means
I see.
Which is the
so
other way.
How do you explain
fewer
that,
boys.
then?
Maybe it's something to do with stress. It's one of these things that's likely to be lots of things that might be affecting it. But this one particular study could hint that it's in terms of the food we're getting and the sort of when times are good and resources are going well. The theory is that if resources are abundant and you've got lots of food and times are good, having boys is better because a boy that is bigger and more manly is actually better himself at having babies. But a weedy man is less likely to do so. So that's not such a good way of passing on your own genes. In fact, when resources and when times are bad, having girls is better. And possibly it's also to do with building up a population after a disaster.
I was going to say, because the one thing that we need to reinforce is that women can have babies and men can't. Men can just make them. So it's better to have a big pool of women
it's the limiting
not having
factor.
babies. And then when times are good, then you make lots of men. And then they make lots of babies using all this population of women that's built up.
The women are needed. Without women, there'll be
no
babies. Without men either. But, the women it's the bottom line that's where they come from. So maybe that's it. It could be. I mean, there's, as I say, likely to be lots of reasons, but that could be one of them. So if you want a boy, if you want to have a go at eating lots of cereal, that might be a way of doing it.
Just to finish here, that on the subject of the landmines, Peter of Carbrook wants to know if is a plural of a mongoose, is it mongooses or mongeese? I think it's mongeese, but what do you think, Helen?
I would go with mongeese.
OK, well, if you have a theory on that, then do get in touch. Email us, chris@thenakedscientist.com.
Laying the facts bare, The Naked Scientists.
You're listening to The Naked Scientist. Now, still to come, we're going to find out how diamonds and other gemstones are formed, where to find them, and how to tell a true diamond from a fake. But first, let's crystallise all that by joining Ben and Dave for this week's Kitchen Science.
As this week's Naked Scientist show is all about diamonds and rubies and rare gems, I've met up with Dave for some kitchen science. Now, hopefully Dave is going to tell me how I can find some of these myself and become rich. So, Dave, is that what we're doing?
Well, Ben, I'm afraid if I knew how to do that, either gemstones would be worth anything by now, or I'd be really rich. So I'm afraid not.
Oh, well we're in your kitchen, so do you have any diamonds here?
No diamonds, but I'm going to show you how to make something kind of similar.
OK, so this is something people can do at home?
Yeah. No problem at all. All you need is some bicarbonate of soda, or ideally washing soda, which is sometimes sold as water softener, some boiling water, a couple of mugs, a couple of forks, some wool and a plate.
Well, this doesn't sound like gemstone hunting equipment to me, so how do we set this up?
The first thing we want to do is make a washing soda solution, sort of about 1 part washing soda to 4 or 5 of water.
OK, and what if we're using bicarbonate of soda?
We can actually convert bicarbonate of soda into washing soda by heating it above about 90 degrees centigrade. So if you pour boiling water onto the bicarbonate of soda and then boil it on the pan for a bit, that will drive off all the extra carbon dioxide and turn it into sodium carbonate, which is washing soda.
So does this mean when we make biscuits using bicarbonate of soda, we're putting washing soda in our biscuits?
You start off with bicarbonate of soda, yes, which then, when you heat it, it breaks down, giving off carbon dioxide, leaving washing soda. This will probably react with something in the biscuit, so it's probably not pure washing soda by the time you eat it.
OK, well, that's a bit of a relief, because I do quite like biscuits, and they've never tasted soapy to me. Well, if we have to boil the bicarb, I guess we may as well put the kettle on. And just while the kettle's boiling, how much bicarb are you going to use?
We want to end up with about 2 mugs worth of solution, so you probably want about a third of a mug's worth of bicarbonate soda.
That's quite a lot of bicarb.
It is, yes.
Okay, so we'll just put the bicarb in an ordinary pan, and it sounds like the kettle's boiled now, so how much water do we need to use?
A bit less than 2 mugfuls of water.
So about 4 or 5 times as much water as we have bicarb.
Yeah, that's about right. It's not critical, but somewhere around there.
Wow, as soon as you put the water in, the bicarb all fizzed up. It now looks like lemonade, actually. Is that the carbon dioxide coming out?
Yeah, that's right. And if we heat it a bit more, we'll get more of it off. So we want to heat it up and wait until it starts boiling properly rather than fizzing.
Okay. And while we wait for our bicarb solution to get to the boil, what's the next thing we need to set up?
What we're trying to set up is 2 mugs with a piece of wool between them sitting into the water at each end.
Does it have to be wool? Could you use string or a nylon shoelace?
It'll work better with something made out of an organic material like wool or cotton string. It might work with nylon as well, but probably better with the wool or the cotton.
Okay, and does this need to be tight between the two?
It wants to be dipping down so it's just below the level of the water in the 2 mugs. You also want to put this on a plate or tray to stop it making a horrible mess.
Well, why would it make a mess?
What it's going to end up doing is pulling water up through the string and dripping off the middle.
Okay, so the plate's just there to catch the drips. So we've got a piece of string that seems to be about a foot long or so, and we place it in both cups.
You don't want the string to fall out of the cups, and one trick you can use, if you tie a loop in each end and then catch it on a fork in each mug, then it won't fall out.
I see, yes, it holds the string right into the bottom of the mug.
And I'll just tie one on the other end.
Well, it sounds like our bicarb solution is boiling now, and it certainly looks to be bubbling away. So what's the next thing we need to do?
Well, now, very carefully, of course, because it's boiling hot water and actually quite dangerous. You want to take this up and pour it into your 2 mugs, which you set up earlier.
So we pour an equal amount into each mug?
Yeah, that's the idea.
Are we trying to fill them?
Near to the top, probably not actually overflowing, so to give yourself a centimetre or a centimetre and a half of kind of safety margin.
And I see that that's submerged each end of the piece of string, the bits that are attached to the fork. Is that what we need?
Yeah, that's the idea. And now you just want to pull the middle of the string down again because it's been pulled down by the water, so it's sagging nicely.
So it needs to be sagging in the middle between the 2 cups, and it actually comes down lower than the level of the water in the cups. How's that going to help us?
Because the string is very attractive to water, the water will stick to it and the string will become entirely wet. Now, if the bottom of the string is slightly below the level of the water, that actually acts as a sort of siphon and suck water from the mugs down to the centre, and you can see a drip starting to form now.
But doesn't that mean the water has to go uphill first?
Yes, it is going uphill, but because it's sagging below the level of the water, there's going to be more water going downhill on that side than coming up on the upside. So the water going downhill will be able to pull the water up over the lump, so it can carry on down and drip off at the middle.
So the water's going to move through the string, pulling the washing soda with it, and then drip off onto the plate. Now, what's this got to do with diamonds?
Well, if we leave this for a couple of days, somewhere warm and dry, like an airing cupboard, we should find out.
Well, we will leave this in Dave's airing cupboard for a couple of days, and for the second part of this week's Kitchen Science, we will come back and let you know what's happened.
That's Ben and Dave, sparkling as ever. Thanks very much. Now, this experiment, like they said, takes a couple of days, but they did this before, pre-recorded, but we'll be back just in 40 minutes. It's all you have to wait to find out what happens. But if you think you know what will happen, or if you've got any questions at all about the science of gemstones or any other science topic, email us, chris@thenakedscientist.com.
Now, Helen, we have to eat humble pie because we were wrong about mongoose. It's not mongoose, unfortunately.
Really?
Troy is listening in Second Life, and he says he's looked on dictionary.com, and in fact it's mongooses. That's the plural.
Oh,
so we were wrong on that front.
All right, sorry.
Another Second Life listener is Pookie Amsterdam, who says, can you program a robot to smell out the landmines? Do you have to use a mongoose or mongoose, gooses, whatever it is, at all? I think probably you could, but you need to rely on some kind of electronic nose, these e-noses, and I don't know how good our technology is at the moment at sniffing these things out with something that's portable and cheap, because the benefit of this was it's very low cost and it is quite disposable. So if you blow up a very expensive piece of equipment, it's obviously a much greater cost to that. Also, Alan in Orpington has a question which I'm not sure of the answer to this one. He says chimpanzees are supposed to have 99% the same DNA as humans. It's roughly that. That's right, roughly. Us humans have to cut and maintain our toenails and fingernails. Do chimpanzees have to do this? I don't know. Do you know? Because
I don't know, actually. It's a good question. I can only imagine they do. I can imagine that they could chew them or something. 'Cause they're quite bendy. They could probably chew their toenails. But we could find out. Anyone got any ideas?
if you have any clues, do get in touch on The Naked Scientist. Chris and Helen, email us, chris@thenakedscientist.com.
Fancy listening to The Naked Scientists in your bed, on your way to work, or even at work? Why not subscribe to our podcast? For more information, visit nakedscientist.com/podcast.
This week, we're looking into the science of gemstones, including how they're made and what they're made of and what types of gemstones there are out there. Now, Ian Mercer joins us now in the studio from the Gemological Association of Great Britain, who's here to tell us a bit more about it. Hi, Ian.
Hello, Helen.
Thanks for joining us. Now, first off, what is it that makes a gem, and how do we know that one is a gemstone?
Well, when you look at a gemstone and you think, well, isn't that beautiful? That really appeals to me and I'll get my husband to spend lots of money on it. Well, that's one of the attributes of gems, isn't it? But also they have to last quite a while, don't they? So they have to be a bit durable or, hopefully, very durable. And I guess pearls are less durable and diamonds are very durable, but they are both gemstones. So it's a bit variable, really.
So it's not sort of a strict definition of a certain chemical compound or anything like that?
It's not that strict, and it depends on those particular factors, and also it helps if they're rare as well. And, of course, it is quite rare to get beautiful big crystals. So, therefore, that's something else that people will pay for and then, therefore, value. And that means it's a gem. But also, they have to be acceptable, don't they? They've got to be in fashion or appeal to your community or perhaps not come from living elephants and things like that. So, how acceptable are they? That's really also a factor. But really, I guess, in the end, it's something somebody pays a lot of money for. It's a gem.
Excellent. Well, I have in here in front of me in the studio a large lump of what I think actually is very beautiful. Chris, I don't know if you agree. It's,
wow, is that yours?
No, it's just something I brought with me. No,
just your engagement
Ian brought
ring.
this in. This is on my thing. No, Ian brought this in. It's a lump of, well, I shall describe it. It's sort of raw crystals, I suppose. It's about the size of my hand, slightly pale blue in colour with some straight edges. What am I looking at, Ian?
You're looking at aquamarine crystals. They are beautiful gem quality crystals, as grown in the earth, very hot, really underneath an area where there are volcanoes. And that's just as it formed. Hasn't been cut and polished.
And
that's the size of Helen's fist. How much would that be worth? Not that I'm thinking of nicking it or anything.
I would guess you could spend something like £100 on a group of crystals like that.
So why are they £100, but a diamond that size would be unfeasibly expensive?
It's partly the rarity value. That's really, how many diamonds do you get on the Earth's surface? Very few. How many big diamonds? Almost vanishingly few.
And what's this made out of?
That is aluminium beryllium silicate. It's got beryllium in it, which is a strange, rather poisonous metal, but these crystals are not poisonous. And it's fairly rare, and it's a little bit rarer when it is that beautiful blue. And it is rarer still if it's in big crystals which are suitable for cutting. And, of course, you can only cut a lovely gemstone out of a lovely crystal. You've got to start with good to get good.
Chemically speaking, what actually are gemstones? What chemicals do you find in, say, rubies and sapphires and emeralds and things?
Well, many of them are what we call silicates, a little silicon atom with 4 great big oxygen atoms around it. If you get those, which are sort of 4-cornered units, tetrahedra, they all link together, often with metals, and that makes up a nice silicate structure, and we think of those as minerals or artificial crystals made as silicates. Now, if those atoms come together really well, perfectly, nice orderly arrangement, then you get a nice crystal. You mentioned ruby and sapphire. Those are oxides. They're relatively simple. That's corundum. Ruby and sapphire are both the same mineral called corundum. And if you have non-gem quality corundum as a sort of sand, that's what many people think of as emery, which is used for grinding and for sandpaper. Yes, yeah. Emery paper.
So it's aluminium, isn't it? It's aluminium oxide.
That's aluminium oxide, yes.
So why is a ruby such a gorgeous red colour and it's aluminium oxide, and a sapphire is that gorgeous blue colour and it's aluminium oxide? What's going on?
What's going on is impurities. Now, you might think, well, how can you call it impure if it's so beautiful? Well, they are metals which get trapped into that structure of simple aluminium oxide. And in ruby, it's chromium. And in blue sapphire, it's iron and titanium. And there are many colours of sapphire, in fact. Many people don't realise sapphire can be any colour except red.
I've got a lovely blue one, actually. I've got 4 on my finger, which I rather like.
Splendid.
And you mentioned that volcanoes. Now, is that where we find all these gemstones? Is that where they're all formed?
Many are in volcanic districts, and strangely, those beautiful aquamarine crystals occurred in pockets around granite. And granite, when it is molten, is a bit like porridge, really, and it works its way up towards the Earth's surface. If it crystallises out nice and quickly around the edge of the granite, then you get those lovely big crystals. If it reaches the Earth's surface, it forms terrible volcanoes, the most awful, dangerous volcanoes ever. Luckily, most of it doesn't get to the surface, and the stuff that stays down there might form gemstones.
So how do we know where to look for different gemstones? And so, in other words, because they require different conditions and quite specialist conditions to form, does that mean that there are hotspots for different types of gemstones around the planet's surface?
There are hotspots, yes. And the type of deposit which forms that aquamarine is called a pegmatite, and those are prevalent in certain places, such as Madagascar, the Ukraine, Brazil, certain states of America, and where there are past or present volcanoes.
And obviously, if you haven't got a volcano now, but you did have one in the past, that means that there's presumably a hotspot there for finding things because those conditions existed once, even if not today.
If it's the right type of rock, right type of volcanic province, yes, that's the place that geologists or gem prospectors are going to look. That's their clues.
And you touched already a little bit on rarity and what it is that we like. And am I right that, in fact, engagement rings, that rubies used to be the one that people wanted because red colour was romantic, it was the colour of roses and hearts and love and things, and that it was only later on that we were persuaded that diamonds were the girl's best friend? I don't know if that's a story I picked up from somewhere.
Well, my wife's engagement ring is ruby. What can I say?
Oh, wonderful.
What does a gemologist give to his wife on their engagement? There's a question. It's The Naked Scientists with Chris Smith and Helen Scales. We're talking at the moment with Ian Mercer. He's from the Gemological Association of Great Britain. If you have any questions, email us, chris@thenakedscientist.com. It is The Naked Scientists with Chris and Helen. Katie's on the phone with Callan, her son. Hello, Katie.
Okay.
Hey, Katie,
Hiya.
how are you?
All right, thanks.
Listening online in Wales, you got a
Yeah.
question about something interesting, sparkly.
Yeah, that's what Callum wants to know. Go on. Say, how are geodes made?
How are they made?
And why do they sparkle?
Why do geodes? How do geodes sparkle? And why do?
Okay, there you go.
So, Ian, the question is about geodes.
Yes.
So you better tell everyone, what is a geode and how do they form?
Well, we were talking about volcanoes earlier. Now, if you think of a volcano after it's erupted and all this black lava comes out and it starts cooling down, then as it cools, some of the gases start fizzing out and they form big bubbles. And those bubbles gradually fill with more minerals as the water flows through the cooled lava. And these minerals line the side of what was the bubble. And because the lava sometimes, or very often in fact, turns to a sort of soil and wears away, you're left with this hard mass, which was the lining of the bubble. And some of those, when they're broken open, you find that they're lined with these beautiful crystals, quite often of amethyst, which is purple quartz.
Brilliant. Thank you very much, Ian. I think I've got one of those. I think my mum's got one in her sort of display case at home. Katie, I hope that helps, and I hope, Callan, that answers your question.
Yeah, thank you.
You're welcome. Thank you for listening.
Thank you.
That's Katie and Callan. They're listening in Wrexham, in Wales. Helen.
And now, what you've all been waiting for, the stone that is said to be the girl's best friend. And I have to say, I have got 3 of them on one of my fingers. But they are the worst enemy on your wallet if you decide you want to buy one for your beloved one. But there are improvements in technology that makes it now relatively easy to produce high-quality synthetic diamonds, which, as we were talking about rarity, means that they're much less valuable. So how can we be sure that when we buy jewellery, it is the real deal? Well, to find out, Mira went to pay a visit to the diamond specialists at De Beers.
Diamonds are forever. A popular slogan and a James Bond anthem. But it's true. Some diamonds were made as long as 4 billion years ago. And it's partly this resilience, along with their incredible beauty, that makes them so valuable in society. But with so many fake diamonds, or synthetics, being made today, how can you be sure that the large amount of money you're parting with isn't giving you a dodgy diamond? I set out to investigate and went to the De Beers office in London to meet with diamond research engineer Philip Martineau from the Diamond Trading Company. I asked Philip how companies like De Beers distinguish genuine gems from fake synthetic ones. He showed me the two systems they use, Diamond Sure and Diamond View. These screen and analyse diamonds by their light absorption and fluorescence properties. The first stage of analysis uses Diamond Sure, a rapid screening machine that identifies 98 to 99% of real diamonds.
The idea underlying Diamond Sure is that diamonds have resided deep within the earth for hundreds of millions of years at high temperatures, and in that time, the nitrogen impurities which are found in the vast majority of natural diamonds have aggregated together into groups of atoms which are more stable, and in the process the way in which the stone absorbs light has changed in a way that we can detect, and in a way that's very hard to mimic in an artificial process on any practical timescale.
So Diamond Sure rapidly screens diamonds using the patterns produced from light absorption, particularly the absorption resulting from nitrogen impurities present in the stone. But samples that don't pass this stage are referred to a machine called Diamond View.
In this instrument, the stones are illuminated with ultraviolet radiation, and the user can then collect an image of the resulting surface fluorescence. And by studying that image, you can determine whether the stone is a natural diamond or an artificial product of a synthesis process.
The surface fluorescence from the UV hitting the stone can be viewed on a linked computer monitor, and the sample can also be rotated for a full three-dimensional analysis. Philip had two samples with him when we met, one real and one fake. So we put them to the test to find out if these machines are as accurate as they should be.
So yes, I've got two diamonds here. I'll put the first into the centre of the sample compartment. It says measuring, analysing, and it gives a result. Refer for further tests.
Oh, so this one's not a real one.
We need to look at it in more detail, but we put that to one side. Put the second on, press the test button, pass. So that's a natural diamond, doesn't need to be looked at in more detail. So I'll take this across to the second instrument, Diamond View. We switch on the ultraviolet radiation, and you can see immediately we have different luminescence coming from different regions of the stone. We can see immediately that this is a synthetic. And because the synthetics are grown in a very different chemical environment from natural diamonds, this is a high-pressure, high-temperature synthetic. It's been grown in a metallic environment. That gives rise to different shapes as the samples grow, and therefore different telltale signals when you look at the sample after growth, having polished the surface back. If we switch off the ultraviolet illumination, you can see that it continues to glow after that, and that phosphorescence is a very indicative thing as well.
Could we see a real one?
Yes, OK, so if I just switch on the ultraviolet radiation again, you can see a sort of tree ring pattern here. So the analogy we often use is if you cut across a tree trunk, you can see rings, each of those rings corresponding to a different stage in the growth history of the tree. And in exactly the same way for this natural diamond here, you have a central region where the diamond started to form spontaneously. As you go further out, you reach a ring where the luminescence intensity goes up significantly. And we know that that's because the environment in which the diamond was forming has changed. It may have moved about in the upper mantle, or it may have been that it came into contact with a different sort of environment because of other material moving into that region. The important thing is that there's a series of those rings, and they relate to the different stages in the diamond's growth. And that's very indicative of a natural diamond formation.
So the complex growth pattern of a diamond, as it formed and moved around the Earth's mantle, can be seen using UV lasers. Synthetic diamond producers attempt to mimic these conditions associated with diamond formation, for technological purposes as well as jewellery imitation. How do they do this?
They're made in a very different chemical environment from natural diamonds. There are two basic techniques: high-pressure, high-temperature synthesis, where they're formed from carbon dissolved in metal solvent catalysts. The metals generally used in some combination or other iron, cobalt and nickel. And the second method is chemical vapor deposition, and there the synthetic materials produced from carbon-containing gases such as methane, usually diluted in hydrogen. And there the synthesis takes place at low pressures, usually at about a tenth of an atmospheric pressure. So again, a very different environment. And it's those differences in the environment which lead to the differences which enable us to identify the material and distinguish it clearly from natural diamond.
That was diamond researcher Philip Martineau from the Diamond Trading Company at De Beers in London, explaining to Mira St-Thellingham how to tell a fake from a real diamond.
And this mongooses thing's going to go on all night, I think. Anne in Long Sutton says mongoose is the British way of saying it, mongoose is American, and both are correct. And Petro tells me that is indeed true.
Excellent, that sounds good.
Glad we sorted that one out.
Thank you very much.
Thank you, Anne.
You're listening to The Naked Scientist with Chris Smith and Helen Scales.
And don't forget, you can also find us on Second Life, of course. Just drop by the Scilands continent. You can look it up and then search for The Naked Scientist. We've got our own HQ there, Second Life Mansion. Now, so far this week, we've found out about how gemstones get made and how the very large diamond companies ensure that the diamonds that we buy really are what they claim to be. But it might surprise you to know that diamonds aren't just about jewellery. They also have some very important technological applications as well. And Chris Wirt is from Element 6, which is a diamond manufacturing and technology company. And he's here to tell us a bit more about some of these applications. Hello, Chris.
Good evening, Chris.
Thank you for joining us. So, what sorts of things can you do with diamonds apart from put them on your fingers?
That's a very good question. Diamond is really quite an exceptional material. It has properties other than its beautiful brilliance that's used for the gem side of it. It's very, very hard, and people know that diamond will scratch glass, but it will scratch absolutely everything else. So there are the traditional abrasive type of applications of cutting and polishing. It's used for rock drilling, for oil prospecting. Where you're basically just using the hardness of diamond. In addition, diamond also has a very high thermal conductivity, so it can be used for the thermal management, for example, of electronic devices.
So in other words, you could use it for heat sinks or something. You could pull heat away from things with it.
Well, it's really heat spreader, so it's exceptionally good at removing the heat from hot spots under, for example, silicon devices. It's also optically transparent, so you can use it for laser windows.
How does that work then? Tell us about the lasers.
Well, you can synthesize the diamond as a polycrystalline plate, and when you get the conditions correct, this plate is perfectly transparent to certainly infrared radiation, and if you can polish it flat and parallel, you can then use it as a laser exit window, and because it has a very high thermal conductivity and a very small thermal expansion coefficient, you really get very little deviation of the beam.
So in other words, that when you make a lens out of a diamond, it doesn't change its shape very much when it gets hot, and also because it's very, very good at conducting wavelengths of all types of light, then it doesn't hold anything back, everything just goes straight through.
Yes, that's pretty much it. Yeah, so you get a much better beam quality through a diamond window than any other laser windows.
The thing is that diamonds are obviously not trivial to find, and not found in big enough quantities to make lasers, so how are you getting around that problem?
Well, in this particular case, the diamond is synthesized by a technique called chemical vapor deposition. That's where you use carbon in its gaseous form. You excite it to a relatively high temperature of a few thousand centigrade, and when you get the conditions right, the carbon that effectively condenses on a substrate forms as a diamond layer.
So how bigger sorts of diamonds can you make with this technique? Are we talking a pinhead, or can you literally make sheets of diamond like that?
No, I mean, you can certainly you can make 6-inch discs of polycrystalline diamond plates, and you can make it millimetres thick. Equally, you can coat surfaces with diamond and use its very hard, wear-resistant properties, if you like. But it's basically many inches in diameter and many millimetres thick.
What is it about the chemistry of diamonds that gives them these amazing properties?
Well, basically it's a very small atom and very tightly covalently bonded in a cubic lattice.
And what does that mean to the average person in the street?
It's very hard, very tightly bonded and very stiff.
OK, but if you were to sort of zoom in with a very powerful microscope and look inside a diamond at the arrangement of the atoms, just very simply, how are they organised?
Well, they're in a tetrahedral arrangement, so each carbon is attached to 4 others. It's very stiff, and because the carbon-to-carbon bond is short, it's a very tight bond. And unlike other materials that we've been discussing on this programme, diamond is just one element. It is just carbon, but it is carbon arranged in a particularly stiff lattice structure.
It's interesting because I had a barbecue the other day and I burned another form of carbon, graphite, charcoal, and that's certainly not very hard. So why is it so different between diamond and charcoal?
It's a different form of carbon. In graphites and charcoals, you don't have this tetrahedral bonding. It's actually in hexagonal plates, and although they're quite strong in one direction, they're very weakly bonded in the other direction. So, in actual fact, graphite can be used as a very good lubricant for that purpose.
So if we took a lump of diamond and heated it up on a barbecue, could you burn it?
Oh yes, it will burn. It is, after all, coal. It's after all carbon, so it will burn like coal if you get it hot enough. It starts to oxidise and form carbon dioxide.
But it'd be a pretty expensive experiment to do, I guess. So what other things are you doing at Element 6? What other applications? Because some of the things on your website suggest things like making speakers for hi-fis.
Well, it's actually tweeters. This is, again, using chemical vapour deposition to lay down a very thin layer of diamond in a sort of not quite a flat plate, but it's a very shallow dome. And because diamond is very stiff and it is relatively low density, you can make a piston, a small piston, that will displace air for the tweeter in a hi-fi system.
So what sorts of sound frequencies will it produce when you do that?
Well, it'll go up to substantially higher frequencies than, for example, a conventional aluminium tweeter, just because of its rigidity and its low mass. It has what they call a break-up frequency in excess of 70 kilohertz, which is well beyond the audible range of human
so that's
ear.
okay if you're a bat, isn't it? But what about for a human?
Well, for humans, in actual fact, the break-up frequency is important because you get harmonics that occur at lower frequencies, and it's the harmonics that the human ear can detect at below 20 kilohertz that make a clattery, tinny sound. So if you have a higher break-up frequency, you actually have a more perfect sound in the whole of the audible range.
And lastly, one other cutting-edge piece of technology you're developing is things to make scalpels even sharper.
Yes, traditionally eye knives, ophthalmic surgery knives, have been made from natural diamonds. We're also able now to make a polycrystalline diamond, which will give almost an atomically sharp edge. So it's extremely good for precision surgery.
Thank you very much, Chris. That's Chris Wirt. He's from Element 6 and telling us there why there's more to diamonds than what just glistens in the eye. Thank you very much, Chris. Now, Ian, there's a quick question here, Ian Mercer. There's a question from Alan, who says Edinburgh is built on a huge block of granite, and you've said that gems can often be found in granite, so why aren't we looking to Edinburgh as the gem mecca of the north?
Edinburgh actually is partly built on, well, the castle is certainly built on the remains of a volcano. Actually, it's a basalt volcano, and yes, you can get gems in basalt, but if you search all the basalts around the world looking for gems, you'll only find gems in very few, relatively speaking. So before you try to seek permission to dig up Edinburgh, I'd think about the geology first.
And there's probably better things to find in Edinburgh, like whiskey, for example. Extremely nice. Thank you very much.
I think I start with that, yes.
It's The Naked Scientists with Dr. Chris and Dr. Helen. If you would like to ask us any questions, we're talking the science of diamonds, gemstones, and anything general, and mongooses by the look of it as well this week. Email chris@thenakedscientist.com. On the way, we'll be solving the problem of where the world's oil's going to come from over the next 100 years.
Stripping down science.
Okay, let's do it.
The Naked Scientists.
You're listening to The Naked Scientist. Now it's time to welcome Diana O'Carroll back into the studio to take on this week's Question of the Week. Hello, Diana. Now, we're talking about diamonds. Now, are you partial to a sparkly diamond, or is that not really your thing?
I do like shiny, pretty things, actually, but they're a little bit too expensive for me, sadly. But
a woman with cheap taste, I don't believe it.
No, I'd love them, really, but I need more money. Please give me money.
Yes.
But if I found an oil well, then actually that would find me quite a lot of money, I think, and I'd have lots and lots of diamonds. So that leads me on to the question of the week, which is from Dr. Raj from Sri Lanka.
During the 1970s, we were told that oil would run out by the year 2000. Then new reserves were discovered, and now they say 2100 is when we will be starved of oil. Is it possible that we'll find more oil reserves in time to come?
So how much longer do we really have before we're forced to find other ways of firing up?
I'm Alistair Crosby. I work as a researcher for the University of Cambridge, and what I study is how the outer part of the Earth behaves on geological timescales. Predictions of the end of oil have a long and undistinguished history. In 1874, the state geologist of Pennsylvania said that all the oil would be gone by 1878. Needless to say, it wasn't. In the 1970s, pundits predicted we would run out by the year 2000, and they were wrong too. The reason why current predictions of peak oil production are almost certainly wide of the mark is that its price has increased hugely in the last 10 years with no reduction in demand. This allows the production of reserves previously considered infeasible. The greater the price, the greater the fraction of a given oil field that can be extracted out of profit. In other words, peak oil depends on price. A good example is the tar sands of Canada and Venezuela. It is only economic to extract the heavy oil when prices are more than $30 a barrel, but the sands in these two countries alone contain more oil than the conventional reserves of the rest of the world combined. More importantly, high prices allow exploration of previously inaccessible areas, such as the deep continental shelves of West Africa and Brazil. Exploration here is amazingly expensive. To drill a single well can cost upwards of $100 million, but the rewards are immense. It may not be politic to say so, but global warming will also keep us in oil. As sea ice melts, huge swathes of the Arctic will become accessible and may contain reserves as large as anything in the Atlantic. It is no coincidence that Russia, America, Denmark and Canada are all aggressively staking their claims. In the end, of course, we will reach the end of what can be viably extracted, although probably not in our lifetimes. But by then, I think we will no longer care. As Sheikh Yamani famously said, the Stone Age did not end because we had a lack of stones, and the Oil Age will not end because we have a lack of oil. We have not invented oil's replacement yet, but I think it is only a matter of time.
Seems there's to be another century of expensive petrol to come, with the more northerly reserves becoming more accessible as polar ice melts away. Here's hoping cheap alternative technologies are unearthed soon.
That's what they're saying in Grangemouth, isn't it?
Now, a regular forum poster, Turnipsock, pointed out that running out of oil might happen next Tuesday because of the current strikes going on. And Graham D said that we'll never run out of oil because it's just become too expensive to extract. Eventually, that's what will happen. Templeton emailed us on the topic of vast oil reserves located in the US. Although this source could amount to trillions of barrels of oil, apparently, it's unfortunately locked away in shale, which is incredibly expensive to process and only yields very low-grade fuel.
Indeed, oil has made a very good fuel for burning, and Fuel Source might answer this next puzzler.
My name's Graham Watson, and I come from South London. And my question is occurred to me when I was listening to the Olympic torch being discussed recently. I was wondering how you transport a naked flame on an aeroplane. It has to be a naked flame, I think, to continue the Olympic spirit. But even without the current security situation, surely it must be quite difficult. But it's obviously possible, so I wondered how they did it.
Well, whacking your head with an Olympic torch might sound pretty loud to you, but why is that?
My name is Bullfrog, and I'm calling from Illinois in the USA. I noticed that at times when I'd put earplugs in to deaden sound from outside, that worked really well, but then the sounds inside my head, they seemed a lot louder. Like chewing or humming or even breathing was really loud. And then I noticed listening to podcasts with the earbud-style headphones in my ears that I couldn't chew breakfast cereal and hear at the same time, whereas if I'm listening to a conversation without anything in my ears, it's very easy to hear and eat at the same time. So I was wondering, why is it when you have earplugs in or headphones like that, are the sounds from inside your head so much louder?
So how can you keep the torch burning without upsetting the aircrew? And why are crisps so noisy? In the meantime, I'll be trying all sorts of different munchy food, but you can email me with the answer at questionoftheweek@thenakedscientist.com or follow the discussion on our forum. That's thenakedscientist.com/forum.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
It's The Naked Scientists with Chris Smith and Helen Scales, and we're talking about the science of gemstones this week. And with us is Ian Mercer, and there's a question coming from Beryl in Braintree about a very unusual mineral, which we'll be finding out in a second. But first, our own mineralogists and what they've been up to this week.
Yes, earlier we left Ben and Dave boiling a solution of bicarbonate of soda to make some washing soda and pouring it into cups. So we shall return to Dave's airing cupboard to find out what's going on.
Welcome back to Kitchen Science. We've had 2 mugs of washing soda solution linked by a piece of string and sitting in Dave's airing cupboard for 2 days now. And Dave is going to show me what's happened. So Dave, let's see what you've got.
Okay, I'll pull it out now.
Oh wow, there's lots and lots of what almost looks like snowflakes all over the string and on the edge of the cup actually. What is this, Dave? Are these little crystals?
Yes, if you look really closely, they're little tiny crystals of washing soda forming on the string.
They're really quite beautiful. They really are like snowflakes, which are little crystals of water. But I can see that you've actually put a third mug in there, Dave. What's going on in that one? It looks very cloudy.
Well, I was feeling an experimental mood, so I thought I'd try some different concentrations of the mixture. This one is with basically as strong a solution of washing soda as I could get. And the string looks really quite boring, but if you pull the string out...
Oh, wow. Where the string was under the surface, there's lots and lots of crystals on there. And the fork is absolutely coated. But why are these crystals forming?
Well, hot water can dissolve a lot more washing soda than cold water. And with this stronger solution, I basically dissolved so much washing soda in there to start with that when it cooled down, it actually had more washing soda in solution than was really stable.
So because you can dissolve more washing soda in hot water, when the water became cold, it had to come out of solution again?
Yeah, it had to come out of solution and form a solid somehow. It's easiest for it to come out of solution onto another piece of washing soda in what's called a crystal. All a crystal is a whole lot of little tiny molecules or atoms all lined up in a repeating pattern.
So they're a regular pattern of the molecules of, in this case, washing soda?
Yes, there'll be a most stable formation for them to be in, and you'll get billions and billions of them all in a regular repeating structure.
So why do we get them forming on the string between the two cups with the weaker solution?
Well, with a weaker solution, there's enough water there to hold all of the washing soda even when it's quite cold. Now, when it moves up along the string, because there's lots of air around it, the water can evaporate. Now, this makes the solution stronger, and eventually to the point where it's too strong to maintain all of that washing soda in solution, and some of it will try and get out. So little tiny crystals will form on the string.
And that's why it looks like the string is covered in snow.
Yeah, and because it will prefer to come out of solution where there's already a crystal, where there's one crystal, it will grow and grow and grow.
If the crystal forming effect is based on the temperature, then why have you had this in a warm place like your airing cupboard?
Because that will encourage evaporation, so it'll evaporate more water from the string, so it'll create the crystals faster. But actually, if you want to make really, really good crystals, you don't want to make them fast, you want to make them as slowly as possible. Because if you try and make them too fast, they'll form lots and lots of small crystals. But if you form them very, very, very slowly, you can actually form a few much larger crystals.
Well, this is a lovely home experiment, and it is quite a beautiful thing to look at. But, I mean, is this really any use?
Well, you'll have used the product of this sort of thing every day if you eat sea salt or sugar. They're both crystals which are formed out of either a salt solution in water or a sugar solution in water.
Wow, so this is how we get salt to put in our food. But is there anything else we can use this crystal forming technique for?
There are thousands of things we use in everyday life which are dependent on crystals. Everything from silicon chips, which are based on crystals of silicon, to fake gemstones. And actually, chemists are very dependent on making crystals to work out what the chemical they've just made is.
Why do chemists need a crystal? Surely they can just use a solution and run their tests on that.
Well, you can do all sorts of chemical tests on it, but if you want to actually work out the structure of the thing you've made, it's very useful to line up billions and billions of your molecules all in exactly the same orientation. And then if you fire X-rays at it, you'll get a pretty pattern, and from that pattern you can work out what was in your crystal.
Isn't this how they worked out what shape DNA was?
Yes, it's called X-ray diffraction, and because DNA is a helix, it had a very distinctive pattern from the X-ray diffraction. They could work out what shape it was.
Well, that's really interesting. Now, you said that sugar and salt and things like that also form crystals. So why did we choose to use washing soda? Why didn't we use something like sugar?
You could use sugar, you could use salt. Washing soda just works a bit quicker. If anyone wants to have a go at this at home with any other dissolvable crystals they've got at home, have a go. We'd love to see any pictures you want to send us.
Well, that's a great idea, Dave. So if you do want to give this a go at home, go to our website at www.thenakedscientist.com/kitchenscience and you'll see full instructions as to how to set this up. And then send in any pictures of your beautiful crystals. Next week, Dave will be live in the studio with the Kitchen Science. So what do we need next week, Dave?
All we need for next week's Kitchen Science is a large rubber band and some lips.
Well, that sounds really simple and also very intriguing. So that's in Kitchen Science next week, but that's all for Kitchen Science this week, and we'll be back with more very soon.
Thank you very much, Ben and Dave. As he says, they'll be bouncing back next week with a mysterious effect on rubber. So there they were, growing some crystals. Now, washing soda will make the crystals much quicker than bicarbonate of soda, which is why they boiled the bicarb to make it into the washing soda. But lots of things will make crystals. Just try them out. Just have a go. And the slower that you grow the crystals, the better the result you're going to get, basically.
We've heard from Beryl in Braintree, who says, what is tanzanite? She's heard apparently that it comes from only Tanzania, which is why it's so rare. Is this true? Ian, any thoughts on that?
The short answer is yes, that's true. Tanzanite is a really beautiful gemstone. It's a gem variety of a mineral called zoisite, which really occurs as a sort of powdery crust, greeny blue and brownish colours, and certainly not gem quality. And that place in Tanzania is the only place in the world where quantities of gem quality zoisite form. And
chemically, what is it?
It's another of these silicates. It's a pretty complex silicate, in fact. Won't go into the formula because it will take longer than a minute. But yes, it's an orthorhombic silicate. It's one of its attributes is that it changes colour as you turn the stone around. It's what's called dichroic. And it's treated in order to improve that blue colour, as with most gemstones.
Wonderful. We've got a text message from Mariana, Ian. She says she saw iolite in a jeweller's window recently. It was a mauve-coloured stone, but she'd never heard of it before. What is it?
This is an interesting stone. This forms at very high pressure. This isn't a volcanic stone. This is a gemstone that's formed as a mineral in rocks that are really being squeezed something. And this is another stone which is intensely dichroic. It changes colour completely as you turn it round.
And just very briefly, where do you find it?
That comes from all sorts of places like Norway and Africa, anywhere where deep-seated rocks are pushed up towards the surface.
Thank you very much. That's Ian Mercer. So thank you very much, Ian Mercer. He's from the Gemological Association of Great Britain. Also, our other guests, Chris Wirt from Element 6, and our production team, I have to say thank you to them, Helen Scales, Petra Minch, Mira Senthalingham, Ben Valsler, Dave Ansell and Diana O'Carroll. Next week is our Science Q&A show, so we'll be answering your science questions. Send them in, chris@thenakedscientist.com. And, as Dave mentioned, in Kitchen Science, we have an exciting rubbery question, which we'll be looking into, so grab your rubber band. Thank you very much for listening. See you soon.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.